welcome to Bite Me. Let's jump into today's video, nerds. Today we're going to be doing referencing and borrowing for our chapter 4 for this live stream. I'm pretty sure this is episode 7. I think this is episode 7. If you haven't been following along, please go to the first live stream that I did, and that one's going to be the beginning of the Rust book. And then you can follow along through all the lives. They're about an hour and a half long, and we're just going straight into Rust and doing projects. I'm also putting out a little mini series this week. It's going to be mini projects based on the Rust book that we've been going through. I think I wanted to put out chapter 2, 3, and 4 because we went through it last week, so it's just going to be following those chapters every week. So stay tuned for that. All right. Let's get started. I haven't live streamed in a little bit, so bear with me. All right. Put on my binoculars. Okay, so last live we talked about borrowing, and now we're on ownership, and now we're on referencing and borrowing. So let's start. The issue with the tuple code in listing 4-5 is that we have to return a string to calling a function so that we can use the string. Wait, let me just make sure I'm in the right one. Okay. So that we can use the string after the call to calculate underscore length. Because the string was moved into calculate length, instead we can provide a reference to the string value. A reference is like a pointer in that it's an address we can follow to access the data stored at the address. The data is owned by some other variable. Unlike a pointer, a reference is guaranteed to point a valid value in a particular type. Okay, I want to go back a little bit. Let's go back to what we learned here. Okay, so we learned about stack and heap. Let me go all the way to the bottom. Just so that it's just a good refresher. Oh, do they not have the summary? I guess it's at the end of the chapter. Okay, so I wanted to give like a small refresher. We learned about the stack and the heap, the differences between using memories or allocating memory on a stack. It's very quick. We already know the amount that is on the stack. The heap, it's allocated in a specific way where we don't know the amount of memory it's going to be holding. And technically you allocate a specific amount or a specific amount of bytes on the heap, and the pointer is on the stack. So you're able to use that pointer to find the information on the heap. I hope that makes sense. The heap is less organized. It is a amalgamation of different things. The stack is very organized. It is like a stack of plates. So every time you put something on the stack, you just add another plate. When you are taking off the stack, you take the plate off the top, and that's how you organize all your code or your memory. My bad. Okay. Ownership rules. Okay, so we did talk about ownership. We were looking at functions that were showing how ownership is used in the scope. And these are the 3 rules. Each value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. And we already see this here. S is not valid. Then it comes into scope. We do stuff with S, and then after these curly brackets, it comes out of scope. It goes out of scope, and it's not valid anymore, and we can't use it. We talked about the string, the big S string, and we're going to be talking about the little S string. Big S string is on the heap. all that memory is allocated on the heap, so it's utilized differently than it is with the little s string. More memory and allocation. Variables, data, interacting with move. So like we were saying before, with putting things in scope or utilizing things in scope, when you move data, it is a bit different. It especially if you're moving data and it's on the heap, it is going to have a different way of utilizing that data, and you cannot have multiple pointers pointing to a value on the heap, because what it does when it goes out of scope is the data becomes invalidated. You can't have two of them because it's going to cause a panic or an error within your compiler because it doesn't know what to do. Okay? What we do is we clone. Here is a clone. This is a perfect example. So over here, we did S1 equals string, which this is now allocated on the heap. Okay? Then we let S2 equal S1, and instead of doing this, which is copying, a shallow copy, we're going to do something called a deep copy or clone. And that's literally cloning the same thing. So when it goes out of scope, when the information becomes invalidated, then we can go and it won't panic. It won't panic because it's cloned. Okay. Okay, memory is freed up. You can copy on the stack only. Okay, so all the things that we're talking about on the heap don't apply to the stack. You can use a shallow copy on the stack and it will not have an error or panic, and your compiler will be fine. Okay. This was a lot, and it was last week, so I just wanted to do like a little bit of a recap before we get into the next one. Ownership and functions. Return values. Okay, this is where we're returning values from a helper function and then returning it in main. Or you're seeing that we're returning a string. Where does it come in? Sometimes this code is a little bit hard to read at first glance. It's easier when I'm going through it, but essentially it's just showing return values using string. Okay. All right, and that was the end. Okay, let's get back to references and borrowing. I just want to do a recap because I forgot what was going on. So I know you forgot too. Okay, the issue with the tuple code in listing 4-5 is that we have to return the string to the calling function so that we can use the string after the call of calculate underscore length. Because the string was moved into calculate length, instead, we can provide a reference to the string value. A reference is like a pointer in its address we can follow to access the data stored at the address. The data is owned by some other variable. Unlike a pointer, a reference is guaranteed to point to the valid value of a particular type for the life of that reference. Okay. I don't know if this doesn't make any sense because we haven't seen any visual aids yet, but it was talking about how the previous chapter we do allocate on stack and the heap. It says we have a pointer usually on the stack that points to something that's allocated on the heap. Now, references is a little bit different because references is only valid for the lifetime of that reference. So, like it says, unlike a pointer, a reference is guaranteed to point to a valid value of the particular type for the life of that reference. We're going to see over here. Here's how we define and use a calculate underscore length function that has a reference to an object as a parameter instead of taking ownership of the value. Okay. So here we have a main function. Oh, actually, let's look over here. They always put the main function first. Let's look at the helper function, which is calculate underscore length, okay? That's what we're talking about. We have function calculate length. remember, the parameter is a coin slot. We don't know which string is, we just know it's a string. Okay, so S equals the string, and we're going to return this usize. But something different here, we have this ampersand, and that is our reference. We're referencing something. Okay, so we're going to return a usize, and then S dot length, so the length of S, and it's going to be an expression. This is everything that we learned in the last chapters. I'm just verbalizing what we've learned. Okay, so function main, we let S1 equal string from hello, and this is our big string. This is going to be allocated on the heap. Let len equal calculate length, and then we're referencing S1 with this ampersand. Okay, this is how you identify a reference. It has an ampersand in front of it. Then we have a print line. The length of S1 is length. Okay, so we're calculating the length of this S1, which is hello. It should be 1, 2, 3, 4, 5. The length of S1 is 5. Okay, so we're going to run this. Okay, so the length of hello is 5. Now first notice that all the tuple code in the variable declaration and function return value is gone. Second, note that we pass in an ampersand S1 into calculate length, and in its definition, we take ampersand string rather than just a regular string. These ampersands represent references, and they allow you to refer to some value without taking ownership of it. We are referring to something that is owning that specific value or that specific variable. This is the ownership. So we're just borrowing it. We're not actually taking it and giving it a new owner. Okay. So here we go. So we have a pointer, which is S. So our pointer points to S1, and this pointer from S1 points to this value, which is hello. And that's how we utilize references. It's just pointing to different things that we're borrowing. Note, the opposite of referencing is known as dereferencing, which is accomplished with a dereference operator, which is, what is that called? A star? I don't know. I don't know what it's called. You can see it. You'll see uses of dereference operator in chapter 8 and discuss details of dereferencing in chapter 15. So let's take a closer look at the function call here. Let S1 equal string from hello. Let length equal calculate length, and then we're going to use a reference to S1. So we're referencing S1. We're just borrowing it, okay? So we have ampersand S1. Syntax lets us create a reference that refers to the value of S1, but does not own it. Because the reference does not own it, the value it points to will not be dropped when the reference stops being used. Likewise, the signature of the function uses an ampersand to indicate that the type of parameter S is a reference. Let's add some explanatory annotations. Why was that so difficult to say? All right. So we have function, calculate length. And then we have a parameter, which is S, and referring to a string. And then that is going to be returning a usize. It says S is a reference to a string. So we're referencing a string and we're returning a usize. Here, S goes out of scope. So we have S.length. So we're using an expression S.length. And then here S goes out of scope. But because S does not have ownership of what it refers to, the S is not dropped, or the string is not dropped. My bad. So the string is not dropped because it's not being, it's not trading owners, essentially. It is just being borrowed. It is just being referenced to. Imagine you're creating a project that you have to do for school, and you have to fill out a reference area. You're not becoming the new owner of whatever scholastic that you're reading. You're just referencing to that website or that book or whatever. That's exactly what we're doing here. The value in which S is valid is the same as any function's parameter scope, but the value pointed to by the reference is not dropped when S is being used because S doesn't have ownership. When functions have references as parameters instead of the actual values, we won't need to return values in order to give back ownership because we never had ownership. We call the action of creating a reference borrowing. As in real life, if a person owns something, you can borrow it from them. When you're done, you give it back, hopefully. You don't own it. You didn't buy it, so it's not yours. So what happens if we try to modify something we're borrowing? Try the code in list 4-6. Spoiler alert, it doesn't work, okay? We cannot modify things that we don't own. If you borrow a shirt from your friend and she said, oh, you can borrow this, and you alter it to fit you the way that you want it to be fit, you didn't buy it. You were only allowed to borrow it. Okay, so we have a function called function change. We have some string, which is our parameter, and we're referencing a string, a big string. Then we have some string dot push string, and then we're adding this world to the end of whatever some string is. Okay, we don't know what some string is, we just know we're adding something, okay? Then in our main function, we have let s equal string from, which is hello. So our string is hello. Now we're going to do change, which is referring to this function right here. So we're calling this function, and in the parameter, which is a reference string, we're referencing s, right? Which is this. Reference s. So what do you think is going to happen? We do a cargo run, some string dot push, and then over here we're pushing world, remember? So we're adding it to hello. We're trying to add it to hello. We're trying to append it, okay? Then we have, okay, so it says some string is a ampersand reference. So the data it refers to cannot be changed. Consider changing this to a mutable reference, which we can do, and we reference mute, not string, instead. So just as variables are immutable by default, so are references. We're not allowed to modify something when we have a reference. Make sure you remember that the majority of the things that are in Rust are considered immutable. Okay, you always have to put a mute in front of it if you do want to change or append or make any type of change to it. Okay. Okay. Mutable references. So we can fix the code from listing 4-6 to allow us to modify a borrowed value with a few small tweaks that use instead a mutable reference. All right, let's get into this. All right, so we have a helper function change, function change. We have a parameter called some string. And we actually have a reference on our mute. You see that there? We're a mutable reference for string. Then we have a some string dot push string, and then we're pushing a comma space world. And we have no idea what some string is. We just know it's going to be a parameter. Then we go into main. Let mute s equals string from hello. So we're actually letting this s be mutable as well. Okay? Then we change. We're calling change, which is this function, and we're inputting a reference mute s. So let's see if this does work. Oh, they never put a print line. I hate when that happens. Anyway, first we change s to be mute. Then we create a mutable reference with an ampersand mute s, where we call the change function and update the function signature to accept a mutable reference with some string and then ampersand mute string. It makes it very clear that the change function will mutate the value it borrows. Now, mutable references have one big restriction. If you have a mutable reference to the value, you can have no other references to that value. This code that attempts to create two mutable references to s will fail. Okay, so we have let mute s equal a string : from, and then we have hello as our string. Let r1 equal a mutable s, and let r2 equal mutable s. Okay, so we're using this twice. Okay, we already know it's going to fail, but why is it failing? Is the question. We're trying to print line r1 and r2. So here's the error. First mutable borrow occurs here. Second mutable borrow occurs here. Now when we print line, we're print lining the first borrow later used here. And that means we can't borrow twice. We can only borrow once. This error says that the code is invalid because we cannot borrow s as mutable more than once at a time. The first mutable borrow is r1, must last until it is used into the print line. But between the creation of that mutable reference and its usage, we try to create another mutable reference to the same in R2 that borrows the same data as R1. It's not allowed. The restriction preventing multiple mutable references to the same data at the same time allows for mutation, but is in a very controlled fashion. It's something that new restorations struggle with because most languages let you mutate whatever you like. The benefit of having this restriction is that Rust can prevent data races at compile time. A data race is similar to a race condition happening when these three behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointers is used to write to the data, or there's no mechanism between to synchronize access to the data. So data races can cause undefined behavior and can be difficult to diagnose and fix when you're trying to track down at runtime. Rust prevents this problem by refusing to compile code with data races. So it just doesn't do it. It just panics and oh, my neck. It just panics and it won't compile it. Anyway, let's keep going. As always, we can use curly brackets to create a new scope allowing multiple mutable references, not just simultaneous ones. Let mute s equals string : from hello, and then we have the scope, and we're doing a variable in the scope called let r1 equal mutable reference, which is S, which is this. Then R1 goes out of scope here. So we can make a new reference with no problems. So we are referencing the same thing, but we're referencing them in different scopes, okay? Because if it's in the same scope, the compiler will panic. Okay, Rust enforces a similar rule for combining mutable and immutable references. This code results in an error. Look, this is a big no-no. Okay, we have S again. We're referencing S here, referencing S here, and then we're referencing a mutable S here. Sorry, I'm like looking at the previous one because it says that if it's in different scopes, it's okay. I don't know if all of these are in the same scope. Interesting. I hope it's not telling us that we can now use references within the same scope multiple times, because that would contradict what we just learned. Okay, we're doing a cargo run. So here we have no problem. Immutable borrow occurs here. Another immutable borrow occurs here. Now a mutable. Okay, that is why. Because if you're referencing a mutable reference multiple times, you would have to have them in different scopes. But I guess if they're immutable, it would be fine to have it in the same scope. That's what I'm understanding from this section. Hopefully that is correct. I'm actually gonna go look that up. Let's look it up after. Let me make a note because I want to know. So the question is, okay, if the reference to is immutable, does it have to be in multiple scopes? And if the reference is immutable, can we refer to it multiple times in the same scope? Because I don't know, I just don't feel like it was explained correctly. Okay, so it says, phew, we also cannot have mutable reference while we have an immutable reference on one and the same value. Okay. Okay. Users of an immutable reference don't expect the value to suddenly change out from under them. However, multiple immutable references are allowed because no one who is just reading the data has the ability to affect anyone else's reading of data. You know what? I got my question answered already. That's nice. And I was about to look that up and everything. Oh my goodness. Reading is fundamental. I do this all the time. I have questions before they answer it in the book. All the time I do this. Okay. Let's keep going. Note that the references scope starts from where it is introduced and continues through the last time the reference is used. For instance, this code will compile because the last usage of the immutable references is in the print line before the mutable reference is introduced. Okay. So we have S, it's bound to hello. We're doing R1 it's bound to immutable reference. Okay, this R2 is bound to immutable reference. No problem, no problem. Then we print line both of them. Then variables 1 and 2 will not be used after this point. Let 3 have a mutable reference to S, and it's no problem. Now, the scopes of the immutable references R1 and R2 end after the print line, where they are last used, which is before the mutable reference of R3 that is created. These scopes don't overlap, so the code is loud. The compiler can tell the difference. It can tell that the reference is no longer being used at the point before the end of the scope. Even though borrowing errors may be frustrating at times, remember that the Rust compiler pointing to a potential bug early at compile time rather than in runtime, and showing you exactly where the problem is. Then you don't have to track down why your data isn't what you thought it was. And that's a really strong point, and that's why Rust is so amazing, because you have such a strong compiler, and she's looking out for you. She's looking out for your best interest for your project and everything. So don't get frustrated when your compiler starts screaming at you because you did something wrong. It is a good thing. It is a good thing. You're catching bugs early, and you are not crashing your code, not crashing whatever code you just wrote at runtime. That's obnoxious and annoying. We hate that. Okay. Dangling references. Oh. In languages with pointers, it's easy to have erroneously create a dangling pointer. A pointer that references a location in memory that has been given to someone else. Okay? By freeing some memory while preserving the pointer to that memory. In Rust, by contrast, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. My bad. Let's try to create a dangling reference to see how Rust prevents them with compile time error. Okay, so we have function dangle. And we're returning a reference to a string. We let s equal string hello, and then we reference s, which is an expression because it has no what? Semicolon. Perfect. Okay, so then we have our main functions. We let reference to nothing equal dangle. Okay, so we're binding this new variable called reference to nothing, and we're calling our function dangle. So you see here, we got a compiler error. So function dangle is returning a string, right? There is nothing really being returned here, okay? It says this function return type contains a borrowed value, but there is no value for it to be borrowed from. Help, consider that the static lifetime, but this is uncommon unless you're returning a borrowed value from a constant or a static. Okay. We'll talk about lifetimes. I think lifetimes are going to be coming up very soon. It is a concept that I'm not super familiar with, but I understand conceptually what it is. Okay. So it's telling you to add a lifetime here and static string. So instead, you're more likely to want to return an own value, which is just a regular string. So it's giving you two different options: take out the reference or add a lifetime. Now, this error message refers to a feature that we haven't covered yet, lifetimes. And you can tell what a lifetime is based off of this right here, that little quotation, that is a reference to a lifetime. We'll discuss lifetimes in detail in chapter 10, but if you disregard the parts about lifetime, the message does contain that key to why the code is a problem. It's because you have a reference on something that is not returning a reference. Do you understand? Let's take, it says this function's return type contains a borrowed value, but there's no value for it to be borrowed from. So there's no reference. You don't need to reference anything. It says let's take a closer look to exactly what is happening at each stage of our Dangle code. So function Dangle, we're returning that string, a reference to a string. Okay. Dangle returns a reference to a string. Let s bind to string : from, and then our string is hello. So s is a new string. Then we reference s. So we return a reference to a string, which is s. Here goes out of scope and is dropped, so memory goes away. And then it says danger. What is danger? Why is it dangerous? I'm scared. Frightened. Because S is created inside Dangle, when the code of Dangle is finished, S will be deallocated. But we try to return a reference to it. This means that this reference should be pointing to an invalid string. That's no good. Rust won't let us do this. So it's referencing S. Hold on. Let me read that again. Because S is created inside Dangle, when the code of Dangle is finished, S will be deallocated. But we try to return a reference to it. This means that this reference will be pointing to an invalid string. That's no good. Rust won't let us do that. Okay. Oh, okay. So yes, we are returning a reference to an invalid string because it's in the same, it's literally in the same function. Okay. The solution here is to return the string directly. So so it's saying that we are using references incorrectly here, right here. We should just be returning it without a reference. Because look at here, we're referencing a string, but why are we referencing a string when there's nothing to reference? Do you understand? Because I understand now. I think I understand now. Okay, this works without any problems. So it's telling you not to reference things that don't need to be referenced, essentially. The rules of referencing, let's recap what we discussed about references. At any time, you can either have one mutable reference or any number of immutable references. And then references must always be valid. Next, we'll look at a different kind of reference. And this is our slices. And this is where we talk about the little s. This is my little s, okay? We've been talking about big S, and these are our string slices. Okay, slices let you reference a continuous sequence of elements in a collection. A slice is kind of a reference, so it does not have ownership. Here is a small programming problem. Write a function that takes a string of words separated by spaces and returns the first word to find in that string. If the function doesn't find a space in the string, the whole string must be one word, so the entire string should be returned. Now, let's look through, sorry, I was just reading the note. Okay, so let's work through what we'd write the signature of the function without using slices to understand the problem that slices will solve. Okay, so we have this function, first word, we have a parameter s, and we inputted a reference to a string, and we're returning a question mark. I guess we don't know what we're returning yet. Okay, So first word function has a parameter of type string. We don't need ownership, so this is fine. Okay, in idiomatic Rust, functions do not take ownership of their arguments unless they need to. And the reasons for that will become clear as we keep going. But what should we return? We don't really have a way to talk about part of a string. However, we can return the index of the end of the word indicated by a space. Okay? Interesting. Okay, so we have a function called first word. We have a parameter which is s, and it's going to be referring to a string. We're going to return a usize, and then within the function we have let bytes be bound to s, which is our parameter, dot as bytes. I'm not exactly sure what the as bytes method does, but we're gonna look at it in a bit. Then we do for. So this is our for loop, which we haven't used in a bit. Our for loop for every I in reference to item. So this is the collection. For I in every reference to item in bytes dot iterate and enumerate method. If item equates to b, I guess this is a quotation space, then return I. Okay. Then we have an expression which is s dot length, so we know what the method length does, and that just shows how long the variable is. All right. I do need a little bit of a break. I actually have a snack. It's just Kiwi. Maybe we should take a snack break. I want to see how long this is. Okay. It's so good to take a little snack break. I'm gonna drink some water. Honestly, I have no idea if anyone actually watches these lives. And that's okay. I have so much fun making these lives. I think it's just easier than making edited videos. I just get a little nervous whenever I have to create an edited video. Because I'm just perfectionist in that sense. Oh my goodness. Why is it all wonky? Anyway. So I'm just a perfectionist in that sense. So it's just a little bit more difficult for me to do those things. Well, I do work through it, and then there's going to be a mini series coming out this week, as I said before, and it's going to be edited, so it won't be so long, and I won't have so many excerpts of me eating snacks. All right. Okay. Let's get comfortable. We're talking about references. No, it's not references. Slices. We're talking about slices now. La la la. Okay. Because we need to go through the string element by element, and check whether a value is a space. We'll convert our string to our array of bytes using as bytes method. So I guess, okay, so in this area with this if statement, so if item equates to b and then space, I guess that's what they're referring to. I think. Okay. So let bytes equal s dot as bytes method. Next, we're going to iterate over the array. Okay, so this as bytes, my bad. Because I'm like, what is this space? What is this space? But they're talking about this variable. Next, we create an iterator over the array of bytes using the iter method. So we're iterating through this collection. So for I and a reference to item in bytes, we're iterating within that collection. And then enumerate, I guess we'll see. We'll discuss iterators more in chapter 13. For now, know that an iter is a method that returns each element in the collection, and that enumerate wraps the results of iterator and returns each element part of a tuple instead. Interesting, I didn't know that. The first element of tuple returns from iterator, enumerate, sorry. Too many big words. From enumerate is the index, and then the second element is a reference to the element. This is a bit more convenient than calculating the index ourselves. Because the enumerate method returns a tuple, we can use patterns to destructure that tuple. And we'll be discussing patterns in chapter 6. In the for loop, we specify a pattern that is I for the index of the tuple and a reference to item for the single byte in that tuple. Oh, okay. Okay, interesting. Because we get a reference to the element from iter and enumerate, we use an ampersand in the pattern. Okay, so item is actually a single byte in the tuple. I was wondering what item was referencing to. Okay. Inside the for loop, we search for the byte that represents the space by using the byte literal syntax. If we find a space, we return the position. Otherwise, we return the length of the string by using s.length or len method. If item equates to b, and then I think this is just a character, which is a space, return I. And then we're also referencing s.length or len. We now have to find out if the index of the end of the first word in the string. But there's a problem. Wait, what? We now have to find out the index of the end of the first word in the string. But there's a problem. We are returning a usize on its own. But that's only a meaningful number in the context of the reference string. Are you just as confused as me? Okay, I'm just gonna keep going, I guess. In other words, because it's a separate value from the string, there is no guarantee that it will still be valid in the future. Consider the program in listing 4-8 that uses first word function from listing 4-7. Okay. Like, I think when you're like reading something and you don't understand, I like reread it in my brain and I'm like, did I just read what I thought I read, or am I just going crazy? Why is this chapter so confusing? Okay. We're gonna keep going because I can't even explain that. Okay, so if we do function main, we let mute s, or so a mutable variable is equal to string, which is hello world. Okay, so let word bind to first word and reference s. So word will get the value of 5. I guess we're utilizing something over here. How do we know what first word is? Using first word function from, oh, okay. Oh, it's over here, it's over here. Sorry, guys. Okay, so first word is, it has a string coming through as a parameter, and then we're returning usize, and then okay, let bytes equal bytes, as bytes, and then we're enumerating. Okay, back to this one. Okay, so main function, we're binding s to string from hello, which is on the heap, and we're doing a hello world, okay? Then we let word bind to first word, and we're referencing s. So word will get the value of 5. Interesting, okay. So s dot clear, this empties the string, making it equal to nothing, okay? Word still has value of 5 here, but s no longer has any content that we could meaningfully use with the value of 5. So the word is now totally invalid. Okay. Okay. Whatever you say. Okay, this program compiles without any errors and would also do so if we used word after calling s.clear, because word isn't connected to the state of s at all. Okay. To try to extract the first word, but this would be a bug because it contains s. Because the contents of s have changed since we saved 5 in word. I'm not sure if I'm just not understanding what I'm reading, or maybe that's it. Maybe I'm just not understanding what I'm reading. Having to worry about the index in Word getting out of sync with the data in S is tedious and error prone. Managing these indices is even more brittle if we write out a second underscore word function. Its signature would have looked like function second word parameter s, which is reference to string, then usize is returned. 2 usizes are returned. Now we're tracking a starting and ending index. We have even more values that were calculated from data in a particular state, but we aren't tied to that state at all. We have 3 unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution into this problem, which is called string slices. Okay. Whew. Sorry, that was rough. That was rough. I did not remember that chapter. I did not remember that chapter. Anyway, a string slice is a reference to a continuous sequence of elements of a string. And it looks like this. So let s equal string from hello world, and then we let hello world equal a reference to s, and the indices are 0 to 5, excluding 5. And then let world is a reference to s, and it's 6 to 11, excluding 11. So rather than a reference to the entire string, hello is a reference to a portion of the string specified in the extra indices that we have here, which is 0 to 5. That's our range. That's our range. We create slices using the range within square brackets by specifying starting index to ending index, where starting index is the first position of the slice and ending index is one more than the last position in the slice. Oh, is one more. Interesting. Okay, so the slice data structure stores the starting position and the length of the slice. which corresponds to the ending index minus the starting index. So in this case, let world equal reference S 6 to 11. World will be the slice that contains a pointer to the byte of the index of 6 of S, which is the length value of 5. So I was correct. So when we are referencing S and then we're utilizing the index 0 it's going to be 0, 1, 2, 3, 4 because we always are starting at 0. 5 is technically excluded. Okay, so it's going to be 0. This is how you would count it. 0, 1, 2, 3, 4. 5 would be kind of like this middle one right here. So we're kind of excluding it. So this would be 5, the space. And then 6, 7, 8, 9, 10. It's excluding 5 and it's also excluding 11. And to include it, you would just put an equal sign in right before it, okay? Yay! Okay, so here we have a pointer. We're pointing to this index, which you can see here. I just actually explained it up here. But this is 0, 1, 2, 3, 4. 5 is excluded. Then we go to 6, 7, 8, 9, 10, 11 is excluded. With Rust range syntax, if you want to start the index 0, you can drop the value before 2 periods. Okay. In other words, these are equal. So it's saying that you don't need this first 0 as a value because it's going to be the same thing if you just put the 2 dots. It's just starting from the beginning. By the same token, if your slice includes the last byte of the string, you can drop the trailing number. That means that these are equal. So let S equal string from hello, let len equal S dot len. So length, let slice equal a reference to S, and then 3 is the starting indice, and length, which would be, I'm pretty sure it'd be 5, because it starts from 1. So the method would start from 1. So it's going to be 3 dot dot 5 equal to len, and then also slice equal the reference to the S, and then 3 as a starting, and then whatever is ending. So that's essentially the same thing, like they are equal. Alright, we're almost done. Okay, you can also drop both values to take a slice of the entire string, so they are equal. So let S equal string, : from hello, let len equal S dot len, let slice equal reference to S, and then 0 as the starting, len as the ending. Let slice equal, and then that's just the whole thing. So the indices is just going to be the whole range. That's why I just stopped off. Okay. String slice range indices must occur to a valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. Just good to know. With all the information in mind, let's rewrite first word to return a slice. The type that signifies string slice is written as a reference string. So we're returning a reference string. So function first word, parameter is S, so it's just going to have a reference to a string or a big string. Then we are returning our reference little string. Within the body, we have let bytes equal s, which was our parameter, dot adds bytes. Remember, that's the amount of bytes. And then we're doing our for loop, so we're doing for this collection and the reference to an item in bytes dot iteration. So we're iterating through it as many times as it is in the collection, dot enumerate, which creates it into a tuple. If item equals b with this character, I guess, whatever this is, I don't even know what that is. And then return a reference to s with this indices 0 to I, which is the collection, and then we reference s and then the whole, which is the whole collection. Here we're indexing the whole collection essentially. So we get the index from the end of the word the same way we did in the last bit of code, I guess. Listing 4-7 by looking for the first occurrence of a space. When we find a space, we return a string slice using the start of the string and the index of the space as a starting and ending indices. Now, when we call first word, we get back a single value that is tied to the underlying data. The value is made up of a reference to the starting point of the slice and the number of elements in that slice. So returning a slice would also work for a second underscore word function. Function second word with the parameter of s and also is returning a string slice. We now have a straightforward API that is much harder to mess up because the compiler will ensure that the references to the string remain valid. Remember the bug in the program in listing 4-8 when we got the index to the end of the first word but then cleared the string so that our index was invalid. The code was logically incorrect but didn't show any immediate errors. The problems would show up later if we kept trying to use the first word index with an emptied string. Slices make this bug impossible and let us know much sooner that we have a problem with our code. Using a slice version of the first word will throw a compile time error. And here we can see function main let mutable s equal string, which is hello world. Let word equal first word with a reference s as a parameter. And then s.clear, which is our error. Then we print line word. Okay, so we're print lining our word, but we already cleared the word, which is invalid. So here we go. Immutable borrow occurs here. Immutable borrow occurs here. Oh, mutable borrow occurs here. And then immutable borrow later used. So, okay, so we're using an immutable borrow as mutable borrow. So it's mutable, that word, we borrow it as a mutable borrow, and then we don't reference it. We just borrowed it as an immutable borrow. Okay, that makes more sense. I hope you're not as confused as I was. I hope you understand more than I do. That's good. We learn together. Sometimes I don't know things, and that's okay. Sometimes you don't know things, and that's okay too. Recall from the borrowing rules that if we have an immutable reference to something, we cannot also take a mutable reference, because clear needs to truncate the string to get a mutable reference. I wonder what clear really does. Okay, so the print line after the call of clear uses the reference in word, so that the mutable reference must still be active at that point. Rust disallows the mutable reference in clear and immutable reference in word from existing at the same time, and the compilation fails. Not only has Rust made our API easier to use, but also eliminated the entire class of errors at compile time. So string literals as slices. Recall that we talked about string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. Let S equal hello world. The type of S here is a string or a string slice. It's a slice pointing to a specific point of the binary. This is also why string literals are immutable, and a string is mutable reference. Now, string slices as parameters. Knowing that you can take slices as literals and string values lead us to more or big string values lead us to more improvement on first world, and that's its signature. So our function first world, we have our parameter, which is a reference to a string, and then we're also returning a string slice. A more experienced Rustacean would write the signature shown in listing 4-9 instead because it allows us to use the same function on both reference to string values and reference to string slices. Function first world, instead of putting our big string there, we're going to put a string slice there, and we're also returning a string slice. If we have a string slice that we can pass we can pass that directly. If we have a string or a big string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of the dereference coercions, a feature we'll cover in the using dereference coercions and function methods section of chapter 15. Okay, defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. Okay, so we have function main. We let my string slice bind to string from hello world. So first word works on string slices of strings rather than whether partial or whole. Okay, so let word equal first word, and we're taking a reference to my string, and we're using indices to take a slice of that string. So here we're doing it 0 to 6, not including 6, and then we have this one who's taking the whole index of the whole world, so it's going to be hello world. First word also works as a reference to strings, which is equivalent to the whole slices of strings. Let word equal first word, and then we're referencing my string, so we're just referencing there. Let my string literal equal hello world. First word works on slices, string literals, whether partial or whole. Let word equal first word, and my string literal. Okay. And we're doing the exact same thing. Okay. I just want to see, it's not printing anything, but okay. Interesting. So essentially it's just showing you the difference in the way you can use string slices. Okay, other slices. String slices, as you might imagine, are specific to strings, but there is more general slice type too. Consider this array. Let A equal this whole array, 1, 2, 3, 4, 5. Just as we might want to refer to a part of the string, we might want to refer to a part of the array. We do this like this. And we've seen this in the last chapter, actually, how to index an array. So we let A, which is our array, then we let slice equal a reference A, and then index the array. So we're also using that reference. Then there is assert equal, which is slice. and then a reference to 2 and 3. So this slice has the type of ampersand, which is a reference to an I-32. It works in the same way as string slices do by storing the reference to the first element and the length. You will use this kind of slice in all sorts of other collections, and we'll discuss this in more detail in vectors in chapter 8. Okay, finally we're at the end of our ownership. I would say ownership is a very lengthy chapter. Yes, it is very lengthy, but it is very interesting, and it has to be learned and taught. Okay, so summary. The concepts of ownership, borrowing, and slices ensure memory safety in Rust programs at compile time. The Rust language gives you control over the memory usage in the same way as other system programming languages do. But having the owner of data automatically clean up that data when the owner goes out of scope means you don't have to write and debug extra code to get this control. Ownership affects a lot of other parts of Rust work, so let's talk about these concepts further throughout the rest of the book. And then we're moving on to chapter 5 when we're looking at grouping pieces of data together in a struct, which I do love structs. And when we are talking about structs, we're going to be utilizing it a lot if you do want to get into creating smart contracts and getting into more of Web3 development. Structs is your best friend. So that's going to be a fun chapter. I do like structs and enums. Okay. So this is the end of the video. I just wanted to reiterate some things that I did say in the beginning of the video. I have a mini series following this Rust book. I encourage you to try out the projects on your own and then go back and look at the solutions once I start putting out those videos. It's definitely going to help with curating your knowledge when we're going through this series. Let me think. I just want to say before we leave that being a nerd is hot, and to keep learning and to keep growing, and you will eventually become a master of your craft. So, hope you enjoy this video. I'll see you in the next one. Bye!